So what we're going to be doing today, we're going to talk about a transfer function, and we're going to say, how can we plot this transfer function? It turned out plotting a transfer function in general is very difficult. Even plotting the magnitude and phase of it would be pretty difficult. So we're going to say, how can we approximate this? And we call it approximation by plot. Basically, if you have a very complicated function, you try to approximate it using linear functions. And we call it the linear approximation of transfer function to by plot. Okay? So let's quickly go over things that we talked about so far. We said if we have any circuit, we can think of the circuit as a system. It has some input that could be voltage or current or like whatever. It has some output, which again can be like voltage, current, or anything. So if we have a circuit, the circuit can be represented in terms of a system. So the system must have like some very nice conditions. It should be like LTI system. And as soon as I have like the input, I can get the output of the system. Then this input and output can be voltage, current, anything. And we said to compute this output, we have to convert the input impulse response system H of t. Yes, difficult. Because you have to compute that integral, and that integral is always like pretty difficult. So instead, we said, this system, the frequency domain. And as soon as we went to the frequency domain, this convolution became multiplication. So if we replace this system with the frequency domain representation of it, I have to replace my input with the frequency representation of it. Transfer that. It's a Fourier transform. If you know how it's compared, just know what's called a Fourier transform. And if we somehow know what it is, for us, we can actually do this. With a circuit with sine waves, we knew exactly like what it was. We had the phasor representation, right? And then the system was represented by H of omega. Omega would be x of omega times H of omega. We said we can compute H of omega, which was the ratio of input. Call this H of omega the transfer of the frequency response. So we call this H of omega frequency response. As soon as we go from time domain to the frequency domain, we're going to have to deal with complex numbers. So this H of omega is indeed a complex function. So if you wanted to plot this, we had an issue. We could only plot it because it was happening on R4. So instead, we said we're going to plot the magnitude of it, or we're going to plot the phase of it. So the magnitude, so to plot H of omega, to plot magnitude of it, and the phase of it. Since this is a ratio, magnitude of H of omega is magnitude of output, magnitude of input. And the phase of H omega is the phase of output minus phase of input. So basically, the complex domain. So this is our complex domain, right? Let's just say this is the real axis and this is the imaginary axis. these functions, x of omega, y of omega, and h of omega, compute this axis, which was our I omega. So all these were a function of I omega. So all these functions are evaluated on this y-axis. And if you recall, for simplicity, I said, let's define this to omega. So what I'm saying is that I'm assuming S is only an imaginary number. It's stopping me from saying S is a complex number, so it has some real part and some imaginary part. What's stopping me from saying that? Nothing. So I can even generalize this to estimate which S is some real number plus some imaginary number. So instead of working only with this y-axis, I'm going to work with the entire complex plane. So I'm going to work with the entire complex plane. And from the functional equation, this estimate is nothing but the Laplace transform. That's basically the Laplace domain. So this S domain over here is the Laplace domain. And since we're talking about the Laplace domain, from this x of t to this x of s, we went from h of t to this h of s, and for this alpha y of s, as this x of t converges to this x of s, and if it converges, what is the region of convergence? It turns out if the region of convergence includes this y-axis, then this frequency response does exist. If it doesn't, means the Laplace transform or S domain exists, but the frequency response does not exist. Okay? Everything exists. I know this y of s is a generalization of this, so I can write it as x of s times h of s. Yeah. So I can compute this h of s, which is the ratio of output in S domain divided by input in S domain. The generalization of the transfer function. Right? So this is the transfer function. The transfer function is the same as frequency response. It's only evaluated in S domain. Right? So it's a more generalized version of the frequency response. Right? For us, since we always define S equals I omega, it's not exactly the same. Let's do a quick example and try to find this transfer function. Okay. Let's just say I am given this circuit. R, and C. The question is, what is the Z omega? Is Z equal to? Nothing but the frequency response. Why is that? Do you remember how we find resistance in general? If I wanted to find the equivalent resistance between A and B, how do we do it? We find voltage across A and B, and then we find current through A and B. Right? How do we divide it? Right? So if I take this to a frequency domain, this is 1 the swing is the same, and it becomes I, the capacitor becomes 1 over I omega C, and this is B. And to find the C equivalent, I need to find AB and divide by count through AB. Right? So I can think of this V across AB as my output, and this I through AB as my input. So this is indeed a transfer function for a frequency response. Right? This is just plug and we know exactly like what it is. What is the equivalent? I have like 3 elements in frequency domain. They're all in series. I can treat them as a resistor. I can basically add them all up. So Z equivalent as a function of omega is N plus I omega L plus omega L C. Simplify. If I find a common denominator, which is I omega C, first term is I omega RC plus I omega squared RC plus 1. Right? I can rearrange it, adding it as I omega squared RC plus I omega RC plus 1 divided by I omega MC. Okay? Again, define this to be I omega. That is equivalent as a function of this. In this case, I omega minus. So I have S squared times RC plus SRC plus 1 divided by S. So this is my transfer function. Right? Turns out here, this transfer function, what is the first thing you notice? The first thing you notice is that if you look at the numerator and denominator, they're both polynomials. They've got different degrees, but nonetheless, they're polynomials. It turns out for all the circuits that we're dealing with, if you write down the transfer function, this transfer function is always division of 2 polynomials. Different degrees, polynomials. This is basically the key to our approximation. So note, before I move on, is that clear how we computed this? Okay. So note, H of S, H of omega, doesn't matter, right? Is defined as H of S equals Y of S divided by X of S, where both Y of S and X of S are polynomials. So let's write it down. H of S is Y of S divided by X of S. So let's say the polynomial that's representing the output is S to the power of n plus a n minus 1 S n minus 1 all the way to n naught. The polynomial that's representing this output X of S is a linear polynomial with degree n plus the n minus 1 S n minus 1 all the way to p. It's coefficients of coefficients. This. The coefficient over here is LC, the coefficient over here is RC, they're like real numbers. So I know L in that A1 all the way to AN minus 1, that belongs to R. B1 all the way to B n minus 1 is also. So what it tells me is that like these two polynomials real polynomials. Real polynomials means like the coefficients are real. You know, polynomials of degree n. And for us, we learned how a polynomial of degree n, this polynomial has roots, right? Roots might be real complex, but none of those have roots, right? Since the polynomial of degree n has n roots on complex domain or complex plane, because both numerator and denominator we can decompose both s and xs, right? Types of like, right? So if I have s to the power of n plus a n minus 1, s n minus 1 all the way to a naught, so this equal to 0, I have two types of roots. N type is just a real root, right? So we have the roots, right? The multiplicity of like it's real root, right? So I have s minus z to the power of like, I have something like this. So I can factor this term out, right? I have complex roots, right? Basically, what it means is that this is complex. What happens if I have a complex root? What do I know about the roots? Let's just say z is the root of this polynomial, and c is complex. What else do I know for sure as the root of this polynomial? These coefficients are real coefficients. So if I have z here, which is a complex number, I must have its candidate as the root to make sure all these coefficients remain real. So if I have complex roots, since all coefficients and this polynomial are real, as a root, therefore z conjugate is a root. So not only do I have terms that are like s minus some real number with some multiplicity, I have some terms that are like s minus e times s minus z conjugate. Write it as some s squared plus some a s plus some b. Right? So what do I know then? If I have a polynomial of degree n, I can use this polynomial to its roots. So I'm going to get terms that are like this, which is just simple, terms. Does that make sense? Yes. So it's pretty good. Why? Because I know I have this polynomial and this polynomial down here. It can be converted into something like this. So I can write. We can write of s as follows. I can write h of s as some constant k to the power of 1 squared plus as plus b to power L2. And terms similar to this, that's my numerator. I can do the same thing for the denominator. So I can write it as s minus p1 to the power of, let's just say, h1 squared plus a prime s plus b prime to the power of h2, and so on. Right? So I can decompose my denominator to simple roots, which means it was real, which means my roots were complex. Let's just define a few things. So definition. H of s is a polynomial divided by a polynomial. If you look at the roots of the denominator, which means the roots of y of s, we call it the zeros, whatever roots we have, we call those roots the zeros of this h of s. So roots of s, which means y of s equals 0, is called zeros of h of s. Right? Just a definition. You can do the same thing for the x of s. The roots of x of s, which is the roots of denominator, is called the poles of this h of s. So roots of x of s is called poles of h of s. Right? For example, let's just say I have h of s that is decomposed to s plus 1 times s squared plus 2s plus 2 divided by s plus 4. Right? Something like this. Right? One my zeros are the roots of the denominator. So zeros equal 1 plus or minus 5. Remember, if I have a root that's complex, I know that the complex either of that root is the root as well, which is exactly the case of 1 plus I is the root, 1 minus I must be the root. What is the pole? The pole is the root of the denominator, so it's negative 4. So s equals negative 4. Right? So what happens? If we have this h of s, we can decompose this h of s in terms of like some constant, times all the zeros divided by the place. It's not good. The ultimate goal is to be able to plot this H of S. Right? If I'm going to plot this H of S, it doesn't matter how I decompose it. I have to plot this multiplication and the division. But I have issues though, because things of this K, which is a constant, I know it's zero. If I know the phase for this term, if I know the phase for this term, I know if I multiply two numbers, the phase for those numbers add up. And if I divide two numbers, the phase would be subtracted. So now, using this, it helps us with the phase. So if I want to compute phase of H of S, it's the phase of K, plus phase of this term, plus phase of this term, minus phase of this term, minus phase of this term. So for the phase, we're set, we're good. We still got issues. We could make this multiplication a summation. But wait a minute, we can't. We can't do that. How? Instead of plotting this H of S and do the H of S, we can take the magnitude of it, take the log of the magnitude. If I take the log of magnitude, it's basically the log of the whole thing over here. Right? If I multiply two things and I take the log, what is log of multiplication? It's just the log of summation. What is the log of division? It's log of the numerator minus the log of the denominator. So it makes my life much, much easier. So everything comes down to the fact that if I can plot these terms, those quadratic terms, unlike the simple terms, then I should be fine. Right? So let's make that note really quick. Properties of log function. One. What is log 10 of 1? 10 to the power of what is 1? 0. So this is 0. What is log of 3b? What we know is log of a plus log of b. Is log of b plus log of b. Right? What's the log to the power of n? We can use property 2 to show this is m times log. Okay. Log of plus b. Absolutely not. We don't know what that is. Okay, so this is not the same as log A, log B. Keep that in mind. What? This property, all these properties, look at enough. If I can write this, well, where did it go? If I take of this, I have log of a constant, which I know what it is. Right? This is a constant. I know log of s minus z1 to the power of L1, which is L1 log of this term. I can say the same thing about this, and these two things are added because of property 2. And then I have like the whole thing divided by this term. So it's just subtraction. So it's pretty good. So it's not a bad idea to try to take a look when you're computing the magnitude. Because of that, we're going to define a whole new scale, which is a semi-log scale. And we call that scale the B scale. Right? So definition. Times log 10 of magnitude of h of omega, which is basically 20 times log 10 of, for example, v out over v in. Right? The scale is of transfer function or frequency response. Right? So in general, I know this h of omega is division of two polynomials. Right? So if we want to find magnitude of it, we're going to look at the 20 times log 10 of magnitude of h of omega, which is 20 times log 10 of magnitude of p1, magnitude of p2. The property 3, this is 20 times log 10 of magnitude of p1 minus 20 times log 10 magnitude of p2. P1 and p2 is still like multiplication, so we know it's like added up. So that's very good. What it tells me is that the only thing I need to know is to be able to like plot magnitude of s minus z1, magnitude of s squared plus as plus b, and things like that. And if I know how to plot those, to plot h of s, I can approximate it by the summation of all these. Right? So we don't have any issues with the phase. Phase, it's like very straightforward. Phase of h of omega, that's phase of p1 of omega, that's phase of p2 of omega. So that's very easy. And this 20 times 10 is not really complicated. It's basically defined as 10 times log 10 2 powers. Right? The power is always proportional to something squared. Right? For example, for r, it's b squared over r. So if I have like 2 powers divided, it's b squared divided by I squared, for example, or v squared divided by another v squared. So I can basically pull this 2 out, and that what's this become 20 times. Then you can see like in some textbooks, you define this in terms of power, but as soon as they define it in terms of power, it is like 10 times log 10. Right? If they define it in terms of voltages or currents, it is 20 times log 10. Keep that in mind. So this is basically on Google scale. So what are we learning so far? We're learning to be able to plot the transfer function, we're able to plot the magnitude, and we're able to plot the phase. For the phase, absolutely no issues. We can plot it. For the magnitude, however, manipulate it a little bit. So instead of plotting it on the scale, Plot it on a devious scale, which is a semi-log scale. We'll define as 20 times log 10. So that's pretty good. So let's go back to our decomposition, right? And see how we can plot all those things. So going back to our decomposition, this h of s has something like this. We have some constant, right? Have some which is s minus 0, we have some at 0, which is over s minus 0 to the power of n or something. Okay? I can combine these two things. I'll write it as s to the power of plus or minus n. And then find if it's like whole zeros, right? For instance, if I have s5 over s4, I have a 0 at 0 of order 5, and I have a at 0 of order 4. So the whole thing is going to be plus. So this n over here is plus 1. If I have, for example, a 0 of order 0 at 0, here, 5 of 0, this is the same as 1 over s, right? Which means this n over here is negative. I combine these. So I can write it in terms of like s to the power of s minus n. I have simple values. I can write it as s over 0 plus 1 to some r1, the multiplicity of this is 1. I can also write it in form in terms of like 2 c1 tau 1 s plus s over tau squared to some power of L2, and so on and so forth. I can write my pairs in terms of p1 plus 1 to the power of h1 plus 2c2 tau 2 s plus s over tau 2 squared h2 and so on and so forth. Right? So all I did was like this. I can basically factor out this z1, bring it down here, and make this coefficient over here 1. And then when I'm multiplying this, it's going to be absorbed with this constant. So I can write it in terms of this. Right? The question is, how can I plot this? Like I said, we're going to take a log, and these become summation and like subtraction. Right? So if I take a log, for example, to plot magnitude of h of s, we're going to plot 20 times log 10 of magnitude of h of s. Right? So it's times log 10 magnitude of h of s equals 1 times log 10 magnitude of k, which is k, plus or minus 10 of absolute value of s, plus 1 times log 10 of absolute value of s over z1 plus 1, plus tau2 times 20 times log 10 of absolute value of this term, 2c1 tau1 s plus s over tau1 squared. And other terms, s 20 times log 10, this h1 comes out, so I have h1 of s over p1 plus 1, minus, again, h2 20 times log 10 of magnitude of this 1 plus 2 c2 tau 2 s plus s over tau 2 squared, and other terms. Right? The phase is that phase of this phase of this. So this was basically simple zero, outcome zero. This is a simple multiplicity album. This is a quadratic zero. This term over here is just a simple pair of P1. And this is a quadratic. Good. To plot this magnitude of h of s, to plot constants, very easy. It's just 5, 6, 7. It's just a number. You know how to plot it. To plot this 10 absolute value of s, and this is I omega. Right? And then you have to be able to plot 20 times log 10 of simple zeros. You have to be able to plot 20 times log 10 of quadratic zeros. And then simple poles, quadratic poles. If we're able to plot every single one of them individually, we know exactly like what this 20 times log 10 of h of s is. Right? But we can add them all together. Right? It's going to be added on top of each other. Right? So the question is, how can I plot these? If I want to plot every single term, if I know how to plot a constant, which I know, if I know how to plot a simple pole, simple zero, quadratic pole, and quadratic zero, I'm done. Right? Also, you have a constant, right? Sort of a break. It's always like constant all the way through. Right? For example, how do we like a plus 5? It's just a simple like line. Right? Zeros, some break. And the break is happening at this zero. And when there is a break, having a zero, so the slope for that is always positive. When we're plotting this, regardless if it's a simple pole or a quadratic pole, the slope is always backwards. It's simple or quadratic, the slope is like downwards, 40 downwards. I'm going to talk about that in details next lecture. Right? But to quickly give you an idea of what's happening, I'm going to call this table 1. Which is going to be next lecture. I'm going to tell you exactly how we can plot every single individual that we have. Now, let's just say I have three different terms. Constant terms, I have zeros. It doesn't matter if it's a simple zero or a quadratic zero. I have zeros. Markers. Magnitude break. Asymptotic slope for magnitude. And then we know asymptotic phase for all these. And that if I have a constant, there is no magnitude break. What is the slope? It's 0. It doesn't change. A constant is something like this. This is constant k. Right? What is the phase of a constant? Again, 0. It's a real number. So there is no phase. If I have a 0, I know the slope is upward, so it's always upward. It's something like this. And it turns out the slope is either 20 dB or 40 dB. That 20 dB is for a simple. 20 dB is for this entire phase is always 90 degrees. This S plus 1, and S is R omega. And the phase is always 90 degrees. For poles, the sun is always downwards. It's something like this. Right? This is slope over here is 20 dB downwards, 50 dB downwards. This is for the simple pole, this is for the quadratic. And then the slope is it's 1 over I omega. Right? So what is 1 over I omega? What is the phase for it? Negative 90 degrees. So the phase over here is negative 90 degrees. And do that mostly for simple pole and simple zeros. Right? For quadratic, it's going to be half of it. Right? So this is the real thing. This is what we know. Trying to get ideas here. If it's a simple quadratic, if it's a zero, it's going to go up. If it's a it's going to go down. But the question still stands. How do we approximate each term? So what I'm going to do is I'm going to give you like a table, which basically gives you an approximation for each term we have over here. So we know the approximation for each term, we know the approximation for the entire function. For the magnitude, which was the hard one, that's basically like the way that's done. So the phase, again, it's not that difficult. The phase is always like adding and subtracting. But the table of next lecture, doing like a few examples, see how whatever we talked about, which was pretty abstract, can be applied to actual transfer function. All right? I'll see you guys Wednesday.